All right, so we're going to talk about the time compressibility interrelationship. So those of you that are working on the end of primary EOP curve, this is important for you. All right. So the objective of this one is for you to well, first of all, to understand how C sub V will change as a function of the overburden stress, because we know that the C sub V is not constant versus time, and then define the secondary consolidation E log P consolidation curve, and then use a sketch to show how you can get from that curve, well, how that curve changes as we go past the end of primary curve. So how the E log P curve affected when we actually have secondary consolidation in the lab. And then finally, qualitatively discuss how we can have both primary and secondary consolidation at the same time. So, and this is pretty much the work of Mesri's work. So, I think this is a review, but so the total volume change as a function of time is that volume change that occurs because of a change in effective stress plus that volume change that occurs at a constant effective stress. And so by definition, that first part is primary consolidation and the second part is secondary compression. So now in the analysis that we told you to do when we're computing secondary compression, we're just going to calculate the end of primary somehow, and there were a couple good questions on how to calculate the end of primary, and I posted a note on the blackboard for you guys to look at. But however you do that, we're going to assume that we reach the end of primary consolidation and suddenly secondary compression starts. But there's really no way to separate the two. There's nothing in the behavior unless primary consolidation is really, really fast. And there's very little secondary consolidation during primary consolidation. You can't. There's no way to tell. So if you're in a situation where secondary consolidation is dominating the problem, there's no way you're going to know, and you think it's all primary consolidation. You're not going to be able to tell the difference. So in the lab, we generally don't have this problem in the lab too much. And why don't we have this problem in the lab too much? Because primary consolidation goes really fast when your specimen's 1 inch thick and doubly drained, or 0.75 inches. The primary consolidation occurs very quickly. So lots of times in the lab, we can make the assumption that there's little or no secondary consolidation going on during primary, but it depends on the material. Okay, so this is again repeat. This is trying to just get us caught up. Tsagi's theory says that we're going to have a void ratio versus log time for a given. This is for a given increment of loading in a consolidation test. It looks something like that. It never gets to zero. If you notice real carefully, the tail end of that curve is actually not flat. It's close to it. We observe that we get something that happens that looks more like that. And if we measure the excess pore pressure, Tsagi tells us it never goes to zero, but we observe that it actually does go to zero. And then on the left-hand side, we really should say this is primary plus secondary. But on the right hand, by definition, if there's no pore pressure, if there's no excess pore pressure, there's no change in effective stress, so that has to be completely secondary compression. So we can measure secondary compression by itself once we're sure that there's no excess pore pressure. But what's happening before then, we really can't separate the two. So what we hope is, on the left-hand side, that primary consolidation is dominating what's going on. If it is, and we can ignore the secondary compression, then we're okay. And we discussed what C sub alpha was. Okay. And then this is how we calculate secondary compression. But again, this assumes that we assumed that all the secondary compression doesn't start until after primary. And I'll briefly discuss the two questions I had about calculating this TP. First of all, that's got to be TP in the field and not TP in the lab, because obviously they don't have anything to do with each other. And then theoretically, what's the time for primary consolidation under Tertsagi's theory? Infinite. So we can't use that number. So there's two approaches to this, which I discuss this online for you. One is to say, well, I'm just going to take my, I'm going to do the normal consolidation, time consolidation thing I do, get C sub V, pick T90 or T95, which are one of the things that are appropriate, call that the end of primary and move on. But more commonly what we do is we just take the end of, we can actually see the end of primary in the lab, or we can use Casagrande's method or Taylor's method to calculate the end of primary. You just take that number and then the difference between what's going on in the lab and the field, if the lab sample is representative, it just has to do with the drainage distance, and you just take the difference of the square root of the drainage distances and convert that time to a field time. So there's two different approaches to it. And then we discussed the C sub alpha values, and said particularly if you look at Mesri and Castro, you get really small values. For those of you guys looking at secondary settlement, who's the secondary settlement team? You're doing end of primary, and you guys looking at secondary? You guys are looking at secondary. Okay. So you should, one of the things that I want you guys to do is look at the C sub alpha over C sub C ratios throughout the whole curve to see if they actually fit in this range. Okay? All right. So this is what I'm saying. You can either assume T90 or T95, or, and the thing I didn't say here, or you can use the lab data. Or use lab TP converted. Well, what you're going to have there is that TP field is going to be equal to TP lab times, it's the H field over H lab squared, right? And I show in the online how to do that if you've got any questions about it. But the rate, you're right, the consolidation time goes as the square of the drainage, maximum drainage distance. So there's two approaches to doing that. Okay, but as we discussed, in reality, we can't separate these two. So even within a single layer, so this is a singly drained layer, and at the top, how long does it take to get for the end of primary? Really fast, or it takes zero time at the very top. Well, so then at the top, that soil starts secondary consolidation right away. Even if secondary consolidation only started at the end of primary, it starts secondary consolidation right away, where down here at the drainage boundary, it's not going to start secondary consolidation for a long time. So even if primary secondary consolidation started after primary in the field, you're going to have different levels of secondary consolidation throughout the whole layer, because it's going to take, every part of the layer is going to take longer for it to get to the get through primary consolidation because of the drainage conditions. So each soil, is then going to follow a different time stress path, if you want to think about it. So there's really no way to separate these two. So let's look at what's happening in our E log P curve. So if this is an E log P curve, and we're starting at this point and going to this point, every element of soil is actually going to go through within that layer is going to follow a different stress path to get down to the next point. The only unique E log P curve is the end of primary E log P curve, and I'll show you that here. So the paths they're going to follow are going to be depending on the loading conditions and the drainage that they undergo. So this is Mesri and Godlewski's work. And so what they did was measure C sub alpha and C sub C throughout the consolidation range for a bunch of natural soils. And they concluded that C sub alpha over C sub C was constant for given soil. We've discussed this already. And that this range was relatively small. And we've actually followed it, we've actually discussed the paper after this one. So the first thing I want to talk about, so you've seen in the void ratio time plots that we've used ones that don't look anything like this, right? They don't have double inflections or anything like that. Well, if primary consolidation dominates in this part of the curve and there's very little secondary, then we always get a curve like this, because if primary consolidation is way more than secondary consolidation, then you won't have too much secondary consolidation until the primary is gone. But what if we load the soil so there's very little primary consolidation? The secondary consolidation is a function of time, not a function of the load, right? Secondary consolidation is a change in void ratios of constant stress. So what if we load the sample just a little bit and there's not much primary consolidation? Well, then the secondary consolidation that's occurring back here will have a more significant effect on what's going on, because you're going to get the same, for the same time, you're going to get the same amount of secondary consolidation, but you're going to have way less primary consolidation. So if you use a load increment ratio, so if you change it, so it's really, the most common load increment ratio in our test is 1, right? You got 200 kPa on the test, you put 200 more for 400. Next one, you put 400 for 800, you put 800 for 1600. So that's the most common we do. And you can show, and Mesri and Godlewski showed this, if you do that, you will always get an inflection curve based on this value of C sub alpha over C sub C. You can show that if you use a load increment ratio of 1, that in the early part of the curve, primary will always dominate and secondary won't, and you'll always get an inflection point in your curve. But if you use a load increment ratio that's less than that, and if it gets way less than 2.5, you're never going to see an inflection point. Why? Because the primary and secondary are about the same order of magnitude, and you're going into secondary right away, very little primary, you're never going to see an inflection point. So a lot of the times when people they're going to tell you to get a different, you get a different E log P curve when you use different load increment ratios. That's because you can't find the right, your E log P curve has a whole lot more secondary consolidation than it does when you use a load increment ratio of 1. So this is why the load increment ratio affects the E log P curve. And a lot of people they'll observe that load increment ratio affects the E log P curve, but without a discussion about why that happens or particular understanding of why it happens. So notice this is the end of if this is the end of primary from the pore pressure measurements, right? You're going to get different, and if you just took these values as the end of primary, that would be the ones for the load increment ratios are just going to have a whole lot more secondary consolidation in them. So you're going to get different answers. If you actually measured the U when the pore pressure is equal to 0 in these, you'll notice that for the smaller samples, the pore pressure goes to 0 sooner because of primary consolidation. And so that's the real end of primary consolidation. But you're not going to find that through a Casa Grande construction or through a Taylor construction because you're not seeing this inflection point that you've got. Because you've got you're convoluting the secondary compression to primary compression to the point where you can't separate them at all. Where in the traditional test, the primary consolidation just overwhelms the secondary so much in the beginning that you can basically ignore it. That's C sub alpha. So you can show that erase this part. So you can show that for our assumption of about the range of C sub C over C sub alpha, that inflection point, or the inflection point theoretically from Terzaghi's curve is 0.7 times E100. So you have to, page up, sorry. So you've got to get a load that gives you a delta E that's big enough to get to that inflection point, or else you're never going to see it, and the secondary is going to take over. All right, so let's talk about what happens in secondary consolidation to our E-log P curve. So let's assume that this is the end of primary E-log P curve. In other words, I did a whole series of tests. I measured the pore pressure. I know I'm not using Casagrande's construction or Taylor's construction. I'm measuring the pore pressure, and I know when the end of primary is for every section. Okay. So I found that point. Now, what happens if I let for the oedometer test that gave me that single point? What happens if I let it go past primary? If I let it go into secondary, what happens on this chart? Does the effective stress change? No, but it's going to continue to strain. So what's going to happen? That point's going to go down like this, right? And then when I reload that, so when I put the next increment on there, it's actually going to have to go. So it's actually over consolidated because I've allowed it to go through secondary compression. And when I reload it, it's actually going to, when I put the next load increment, it's actually going to load it along the reload curve because I basically pre-consolidated by allowing it to going into secondary compression. And it's going to go on the reload curve and then back down the primary curve. If I do that one, it's going to load like that. So what happens, for instance, here, if I put a small, if I'm at this point and I put a load increment ratio that's small, I'm actually just going to load from there to there. So, I mean, this is one of the problems with small load increment ratios. If I don't give it a load increment ratio that's big enough to get over whatever the pre-consolidation stress I created by letting it go into the secondary compression, I'm not actually measuring what's going on in the virgin curve. I'm measuring some reload thing that I don't even understand because I didn't think it was over consolidated. Anyway, if I let every specimen, every load increment go past primary by some amount, I'm going to get an E-log P curve that's got more deformation in it than the primary E-log P curve is. And if I let them go even longer than that, I'm going to get another one like that. So this is one of the problems, and you'll find this as you guys analyze the E-log P curves that you got were from the 24-hour test. And you'll find out that if you go back and calculate the primary correlations, you'll see exactly this. So what's going on here? There's two things. There are two really important things that are going on here. What's changing as I allow the consolidation test to go past the end of primary? Yeah, your sigma prime C, it appears to be changing, right? At least the way we determine it. And it seems to actually be decreasing. So the soil is starting to look more normally consolidated, right? And the other thing that's happening is C sub C is changing. That's just because, that's nothing to do with the soil behavior, that's just because of the way we measured it. So these are presented from your text about so there's not a lot of discussion in your text, but I just want to show you this actually there. So what happens if you use small load increment ratios? Notice with small load increment ratios, you tend to get less displacement than you did with the larger load increment ratios. Well, that's because if your load increment ratio, you're not necessarily loading out to the virgin curve all the time. It depends on how much secondary went in, and secondly, because it includes secondary consolidation. And then this is a good example of the difference between using the 24-hour and the end of primary consolidation. Notice that your stress strain curve is kind of softening, and where you're gonna compute signal prime C. First of all, it's gonna be harder to define because you won't have as distinct a curve, and secondly, it's gonna be you're gonna get a softer soil. You're gonna get calculate more settlement than you would get from the primary consolidation curve. So let's talk about this in 3 dimensions now. So let's talk about if we could separate void ratio change in terms of time from void ratio change from primary consolidation. So if this is our end of primary consolidation curve, okay, this is the one we got by determining where the end of primary was and plotting that curve. All right. Then we could have if we allowed the soil then to go into secondary consolidation, we could get a whole bunch of different curves that each allow more secondary consolidation. And if we know what, so this is C sub C, and in this direction, this is C sub alpha. And if we believe that C sub C over C sub alpha is constant, which is Mesri's thesis, we can actually calculate, if we can measure C sub alpha at the end of primary, and we know C sub C, and we can measure the end of primary C sub C, we can actually reconstruct these curves. Because we know how to measure C sub alpha. We just wait for the pore pressures to be gone, and then by definition, any deformation we get out of that secondary compression, because there is no primary consolidation after that, right? And then we generate the end of primary E log P curve, and we know what that is, because that's unique. That's the only E log P curve that's unique, is the end of primary one. All the other ones are arbitrary by some standards. So we're going to generate the end of the primary E log P curve, and we measure C sub C all the way. And then after the end of primary, we're going to measure C sub alpha, and we know C sub alpha. And we'll calculate the C sub C over C sub alpha ratio, and we assume that it's constant for the soil. Then anywhere I go in this curve, at any point in this curve, I know at this point C sub C is like that, and I can calculate this C sub alpha. At this point C sub C is this, and I can calculate this C sub alpha. And I can reconstruct every one of these E log P curves. So each of these is for end of primary plus some amount of time past primary. So what makes this possible is the assumption that C sub C over C sub alpha is constant, because without that we can't do this. So what are the implications of this? Well, so the lab measurements we make are dependent on the interaction of primary and secondary consolidation, because they really are both going on at the same time. And if we don't understand that, we don't run the lab tests right, then we're going to get really poor estimates of the field behavior. And the end of primary is the only unique stress strain curve for our soil. I'm not saying it's the one that's necessarily the right one to use in all circumstances, but it's the only unique one that's available to it. You've got to run if you run your laboratory test with load increment ratios of less than 1, then there's no guarantee that unless you have absolutely no secondary compression, there's no guarantee that you're actually going to see your inflection points, and you're not going to understand the data. And you could come up with, in that case come up with E log P curves that are stiffer than the end of primary or less stiff than the end of primary, depending on what's going on. If you're in the situation where your load increment ratios are so small, to go back to this figure, if you're in a situation where your load increment ratios that you've allowed it to go into secondary compression, and then you run it with the load increment ratios that's so small you don't get back out to the Bergin curve, you could actually calculate settlements that are less than you expect. So it depends on what's going on there. So the load increment ratio can really confuse your measurements. And then finally, this assumption that the secondary starts after primary. it's only accurate for soils that yeah, I'm not sure I said that right. I think about this for a minute. It's probably only important. A better way to say it is for soils that have for when primary dominates the total sediment. I'm not sure it's accurate to say it this way now that I think about it. It's only accurate for soils where primary dominates. Because when primary dominates, it's okay to assume there's very little secondary compression, and then whatever secondary during primary, and then during secondary you can calculate it. So the uniqueness of the E log sigma curve. So I'm not even sure why that slide was in there now, come to think of it. I don't know why that one's in. Oh, how do we do this? Okay, sorry. So how do you do this? Well, you determine the E log P curve. You determine the end of primary curve. You don't actually have to make pore pressure measurements to do this. You can, as long as you're using a load increment ratio greater than 1 and you're getting inflection points, you can just use Casagrande's method or Taylor's method. But you've got to determine the end of primary E log P curve. Okay? Then you measure C sub alpha for several points along the E log P curve. And realize the C sub C is going to be changing along the E log P curve, right? You're going to start off and reload. Let me go back here. This is probably why I put this here. So up here, when I say C sub C for this person, I'm just talking about the slope of the curve, whether it's in a reload section or so. Up here, this slope is going to be very small, so the C sub alpha is going to be very small. And when you get to here, C sub C is increasing, so if you believe that C sub C over C sub alpha is constant, C sub alpha is going to. So here, if you let these run past primary, you're just going to get a little bit of secondary settlement because C sub alpha is pretty small. So that's going to happen along here. You're going to get very little secondary. But when you get to here, if C sub alpha and you let it run past primary the same amount, you're going to get more secondary. And out here, you're going to get the most secondary compression. And then out here, when the soil starts to stiffen up and C sub C starts to decrease again, you're going to get less secondary compression, assuming you let it run past primary for the same amount of time. So not only is C sub C varying along this, but if you believe Mesri's theories, then C sub alpha is also varying. So the way that you can determine what's actually going to happen is you calculate the end of primary E log P curve, and then at several points along there, you're gonna measure C sub alpha. So you're gonna let several of those increments run into secondary and measure C sub alpha. You know C sub C from that point in the curve when you're done, and then you're gonna calculate the C sub C to C sub alpha ratio, which according to Mesri is unique for your soil. This all assumes that you believe that C sub alpha over C sub C is unique. If you want to, you can estimate it based on Mesri and Kasher. We talked about that. And so now what you're going to do is you're going to draw, using the C sub C over C sub alpha, you can plot new E log P curves for any time after primary that you're interested in. You can do it for T over TP of 10, T over TP of 100, TP of 1,000. And then, so I can come back to my curve here. Let's see. So I can come back to this curve, and if I know C sub C over, is it C sub alpha over C sub C, C sub alpha over C sub C, right? If I know this, and if I know that value, and I've calculated my end of primary curve, I can come for a T over TP of equal to 10, in other words, 10 times the end of primary. I can calculate how much secondary I'm going to get at each one of these points, right? And I can draw a new stress-strain curve for T over TP equal to 10. And then I could do the same thing for T over TP equal to 100. So I'm just going to come up here, I'm going to wait longer, I'm going to get more secondary settlement. And I can draw a new E log P curve for T over TP equal to 100. So what I'm really doing is I'm plotting, so if this is the EOP curve, this one might be T over TP equal to 10, and I'll just pick an arbitrary one. This one might be T over TP equal to 100. You understand what I'm doing, at least conceptually? So now, so what I can do is I get a different stress strain curve for each of these, and then if I want to calculate the settlement in the field for a certain time after primary, I have to calculate what the end of primary is going to be in the field, and I could just pick, rather than trying to calculate the secondary settlement in all different places, I can just, or trying to calculate secondary settlement after the end of primary, I can just go into the stress strain curve for that ratio of T over TP that I'm interested in the field, and I can estimate the settlement of the field after primary. So that's not a rigorous way to do it, but that's one way to calculate. That's one way to calculate. Ooh, that should be. Yeah, that's right. Using E. Yeah. So the way to do this is you're gonna do your settlement versus time using primary consolidation the way we've always done it, and then to estimate the settlement you get at some later time, you're going to use these E log P curves for the later times to calculate how much secondary settlement you're going to get. So, some summaries of looking at it. So, yeah, I'm not sure. I don't think there's any fundamental behavioral. If you talk to, so these are all Mesri's theories. If you talk to Mesri, he'll tell you that he's just an observationalist. He gets really, really high quality data. He looks at it, and he looks at lots and lots of data. And he's just reporting. He's not a behavioralist. He's not. I don't think there's any. As far as I know, there's no theories that show you that in log time that these consolidation curves can behave this way. He's just telling you what he observes, and he'll be the first person to say that. So this all this depends on if you buy into Mesri's consolidation theories. But if you do, it explains a lot of the behavior that we see. It explains why if you have small load increment ratios, you don't see inflection curves. And it explains why that if you let the E log P curve go past the end of primary, why you appear to get pre-consolidation stresses that get smaller. And it explains a lot of this behavior. I'm not sure that it's fundamental consolidation behavior, but I do think it's a useful way to look at stuff if you're in a situation where there's potentially going to be a lot of secondary compression. So I wouldn't be afraid to use it, but I'm not I'm not a true believer. Maybe that's the way you say it. Anyway, so what do we know from this stuff? Well, you definitely want to use load increment ratios greater than 1, or else you're going to have a real hard time putting an E log P curve together that makes any sense. So always run your test with an E log P curve greater than, with a load increment ratio greater than 1. There really is only one unique E log P curve, and it's the end of the primary one. All the other ones are arbitrary by some standard. If there's not a lot of secondary settlement in your soil, then maybe it's not much difference, but they're definitely not the same. And you'll see even when these guys show you their E log P curves that they get from end of primary, you'll see the difference between the one that they've got and the one that you guys all use. And you can make your own decision about whether it's important. So in order to do that, you've got to actually determine end of primary and take the data at this point. So I'm an advocate of doing end of primary E log P curves, even if if only for the reason that it's the only unique E-log feature. And it's not that you need to measure pore pressures. You can do it using Casagrande's or Taylor's methods. You don't have to have a fancy consolidometer and do pore pressure measurements. So I think you should, even if you're running a 24-hour test, I think you should go back, find in the primary for every increment, and plot the end of primary E-log peaker. If you're running test past E-log peaker, there's several things that are going to happen. First of all, it's going to appear to reduce sigma prime C, which kind of goes back to Wesley's and Yanbu's discussion about, well, what the heck is this sigma prime C anyway? And it's maybe just, conceptually we understand why it's there, for soils that are loaded and unloaded, but measuring it off an E-log P curve is not a very good way to do it. And it'll also appear to soften the E-log P curve. The one thing I think that is pretty obvious from field behavior is those soils that have high compressibility also have high secondary compression. And I think that just has to do with the structure of those soils that are highly compressible have a lot of void space, and once you disturb them, they've got a lot of opportunity to rearrange themselves and undergo creep. Mesri's data shows that the original Mesri data from the 77 paper or 73, I can't remember now. That was just the water content, it's plotted on a log space and its water content. Now that's not very good data, but the more recent stuff, the stuff that he got a couple of decades after that and that are presented like in Mesri and Castro are pretty good data, and they show that the C sub C over C sub alpha ratio is pretty constant. So if I had to measure secondary compression or predict it, I wouldn't hesitate to use that information. And I think I would even go beyond that and say, I would just assume you're going to get that, assume this value, and go see whether the secondary compression is going to be important for your problem. There's no reason not to. It's a pretty simple calculation to do, and you don't really need any data. You just pick C sub alpha or C sub C equal to 0.35 or 0.4 and press on. All right, so that's a really brief 30-minute summary of all of Mesri's works, which it doesn't do him justice, but